remember that we are making a change of variable here. So the x size ij, we are going to this lambda 1, lambda n, and this yj elements. Okay. So this is the differential element of that. So from this I have to calculate the Jacobian. So for example, just take the example. Yes. This guy? No. See yeah, sure, it's a change. But d lambda I. So I'm saying that when I make a change, right? So I'm making a change in all these variables. So d lambda 1, so you have the differential element d lambda 1, d lambda n, and there's dyj's. All of them are changing. Okay? So that's what it means, when I write down this d of lambda means when I make a change of coordinates of lambda i's and yj's, what's the sort of change in the Jacobian? This guy? Of course it's diagonal. Because remember I started out with this, right? This is always diagonal, but it's a diagonal, but it's, if you like, it's a function of time. At each time t is a diagonal. Okay, maybe you are not following the logic. So again, just think what I'm doing. So I'm saying that imagine, okay, think of a fictitious time, okay? You have xt, ot, this is transpose. So imagine that there's a fictitious time, okay, which is varying, let's say. Okay? So you started at time t equal to 0. You started out with x of t was identity matrix. Time t equal to 0. So at time t equal to 0, your matrix O was identity also. And this guy was also a diagonal matrix, whatever it was, which was x0 itself. Okay, fine, x0 is diagonal if you like, some lambda 0. Okay, is that fine now? So now I change, imagine that you increase the time, it's incrementing. So the time is incrementing, this x is changing a little bit, O is also changing, this guy is also changing, but this guy is always diagonal. Because this is by definition, right? At time t, this is a different t here, but this is the orthogonal transformation, right? So the lambda of t is the diagonal matrix that you obtain by diagonalizing x at time t. So this relation is valid at all time t. Clear? Okay, so we have this, and once we have that, so let's look at some example what it means. So suppose again, I've had to take n equal to 2 example. So n equal to 2 example means dx11 is d lambda 1, right? Because I put I equal to j equal to 1, so this is 1, so d lambda 1, and when I equal to j, these guys vanish. Okay, so I have just this. What about dx12? So dx12, when I is not equal to j, so there is no contribution from here, and this guy is just lambda 2 minus lambda 1 times d12. And dx22 is d lambda 2. Right? So what's the Jacobian then? Jacobian is just dx11 d lambda 1, so that means you will have a 1 here, then 0 0 because there is no other element there. For this guy, this will be okay. Maybe just to not to confuse you. determinant of that matrix, right? So that's the Jacobian. So what is it? We just read off from here. So dx1 on d lambda 1 is just 1. dx1 on d lambda 2 is 0, because there is no things there. This is 0 also. dx2 to d lambda 1, 0. dx2 to d lambda 2 is 1. And you have 0. So here, dx1 to, sorry, this should be lambda 1. dx1 to d lambda 1. Okay? So that is just 0 again. dx2 d lambda 2 is 0 again. And this guy, dx1 to d1 on 2 is lambda 2. So this is the Jacobian, which is lambda 2. This is the result we derived earlier using cosine theta rotation matrix. Okay. So now you see it just follows from this. So now if you go to, this is very easy to generalize now. If you go to n equal to 3, let's work out the case n equal to 3. What do I have for n equal to 3? So remember, my original matrix was for n equal to 3 was x11, x12, x13, x12, x22, x23, x13, x23, x3. So the independent elements were these 6 people here. So from this relation, you have dx11 is d lambda 1, dx22 d lambda 2, dx33 d lambda 3, and then you have dx12 is lambda 2 minus lambda 1, and d012. So I went from these 6 variables to a new set of 6 variables, lambda 1, lambda 2, lambda 3, and this O12, O13, O23 from the x sides. Okay. So I can read off the Jacobian. So the Jacobian would be, you can check, this will be a 6 by 6 matrix. Basically it will be 1, 0, 0, 5 zeros, then again 0, 1, 0, 0, 1. Third one is also 0, 0, 1. These are the corresponding to these 3 guys. And then you will have 0, 0, 0, and here you have lambda 2 minus lambda 1, and then 0 again. Then 0, 0, 0, lambda 3 minus lambda 1, and then 0, 0, and 4. So it's a diagonal matrix completely. I am not writing it very well, but there are 6 elements, 6 by 6. Okay. So you can fill up the things. So it's a diagonal matrix basically. So 1, 2, 3, 4, 5, 6. And the last guy is just 0, 0, 0, 0, 0, and 3. Okay. So these 3 elements correspond to these 3 guys here. So basically, the Jacobian matrix is completely diagonal. Okay. So you can read off the determinant easily. If I take the determinant of that, so this just becomes lambda 2 minus lambda 1 modulus. So n by n case, exactly same. So it will be a diagonal matrix. The Jacobian will be a diagonal matrix in the n by n plane, and the diagonal element, non-zero diagonal element, which are not 1. So there will be n of them will be 1, and the rest n of them, n into n minus 1 of them will be just these factors essentially. Okay. So So therefore, we arrive out at our final result, which is we call the famous Wigner-Dyson distribution, which is the joint distribution of eigenvalues for n by n real symmetric matrix will be up to some normalization exponential for Gaussian case. So this object here is just this analog of the Gaussian, for example, but it could be, as I said, it could be anything, any rotational invariant potential basically. So, but let's write for the Gaussian case. So this will be half of summation lambda I squared. So that's the usual standard part where you replace the x's by the new change of variables. And new change of variables, it does not involve the eigenvectors, only eigenvalues, and therefore you have that part. And then there's the Jacobian part. Which is, just as we proved, that this is lambda I minus lambda j modulus. So this is called the Gaussian orthogonal ensemble. Orthogonal ensemble means, because it's a real symmetric matrix, these correspond to real symmetric matrices, and they are invariant under an orthogonal rotation. Okay? So, and of course, what you notice also because of this, I mean, as I mentioned again many times, that it does not depend explicitly on these elements D1, these O1, 2, 1, 3, O2, 3, etc. So that means eigenvectors decoupled from the eigenvalues. So you can integrate over the eigenvectors. You don't care about eigenvectors, and just look at only the eigenvalue distribution. And so this is the eigenvalue distribution. Okay. Now you can repeat the same exercise for complex Hermitian matrices. So that means I have a X matrix, which is a complex Hermitian matrix. I can diagonalize it by unitary transformation instead of orthogonal. Now you can diagonalize it by unitary transformation. Which means U dagger is same as U dagger U as unity, identity matrix. In the case of orthogonal, this was just a transpose, and here it's just a Hermitian conjugate. So again, you repeat the same exercise that I did. Okay, so this I leave it as an exercise. Okay. So imagine you introduce this 50 such time. You start with an identity matrix, and you just evolve it, and do follow the exactly same steps as I did for the orthogonal case. And you can write down the 2 by 2, 3 by 3, etc. And you will find that the general formula for joint distribution of n eigenvalues for the Gaussian case would be again up to some normalization constant, which I am not writing for the moment, will be exactly same. This factor doesn't change. Only thing that changes is the Jacobian. Okay? The Jacobian now becomes lambda I minus lambda j squared. Just do the 2 by 2 case first. Okay? Exercise. Start with the 2 by 2. And for 2 by 2 again, you do not need need to go through all this procedure. 2 by 2 again, you can define a 2 by 2 unitary matrix, the SU2 matrices, and you can just do it by hand basically, and find out calculate the Jacobian and show that it is actually lambda 1 minus lambda 2 square. And then you follow the same steps and generalize it to n by n. Okay. So this is called the Gaussian unitary ensemble. short is, often in papers on random matrices, you will always see this GOE, these three ensembles. This is called the GOE, this is called the GE, Gaussian unitary ensemble. And then there's this third case, which I did not discuss at all, which also has real spectrum, which is called the third example. So this is this quaternion matrices. It's called the quaternion self-dual matrices. I'm not explaining this, but it's more or less similar. I mean, you just have to go through the similar algebra. So here, the analog of the unitary or orthogonal matrix would be something called symplectic matrix. So you can diagonalize again by a symplectic transformation, and this is called the the conjugate, like the Hermitian conjugate of U. This is the self-dual conjugate of the symplectic matrix. And if you follow the same exercise again up to some normalization constant, the answer for the joint distribution of eigenvalues would be exactly same, except that this should be power 4. So this is called the Gaussian symplectic ensemble. GAC. So these are the three standard Gaussian ensembles, the Tyson's threefold way. So this is called the GOE, GUE, and GAC. So as I said, remind you that Gaussian ensemble is a very special case, which is rotational invariant, as well as that the matrix elements are independent of each other. So you can think of this as remember the picture I was drawing there, that there are two types of matrices, random matrices that we can consider. So this is in general called Wiener matrices, which means matrices with independent entries. IID or whatever independent entries. And this guy are the rotational invariant ensembles, rotational invariant matrices. Meaning that the joint distribution of entries is completely invariant under a rotation. And in this overlap region, there is only one guy, which is the Gaussian, which is both independent entries as well as rotational invariant. And again reminding you that this whole exercise we could do only for rotational invariant example. Okay? So in general, so let me just say that in general, if I go beyond Gaussian, for instance, I could choose by this object here, the entry distribution to be proportional to exponential minus half, and then trace of some polynomial g of x. If you choose this, x is a matrix. So if you choose this polynomial v of x to be just quadratic, then you are back to the Gaussian ensemble. But you could choose, x to the power 4, for instance, and so on. X to the power 6 you can add. So this is exactly like the 5, 4, 5, 6 theory that Shumita was talking about yesterday. So these are called the potential. You'll see this is in the matrix space. Okay, this is not just a scalar field. This is a matrix, and so these models in general are called the matrix models. So this is like exactly like choosing the potential in 5-4 theory. Okay? So if you choose, this is the analog of the Gaussian free field theory, Gaussian free field that Shumita was talking about. And then you can add the 5/4 term, then the 5/6 term, and so on. So same thing you can do in matrix models. Okay. So the potential, this is the analog of the 5/4 potential. So the potential you can actually choose by adding different terms and so on. Now in all these cases, so because of this trace structure here, trace of all these guys, okay, when you make the similarity transformation, so clearly this object is invariant under rotation. Okay? However, whenever you are departing from Gaussian, for example, when you add some x to the power 4th term here, you see immediately that if you now write, everything in terms of the matrix elements, you can no longer factorize the joint distribution into individual distribution of entries. Only when you have quadratic term you can do that, but when you have add the quartic or cubic or whatever any other higher order term, you can no longer do that. Which means that these correspond to matrices where these entries are highly correlated in a way such that when you make a rotation or change of basis, that the probability distribution is invariant under rotation. But that means necessarily that they must be highly correlated in order for that to happen. So for such rotational and invariant examples, matrix models generally, so if I can ask, what's the joint distribution of eigenvalues? So again, up to some normalization constant. So as I said, this part you are again think of making a change of variable. So when you make this change of variable, because of this polynomial structure of this, so trace of that, so you see that this guy depends only on the eigenvalues. So this will be just e to the power minus half summation I v of lambda I. We can check that because if you check, when you write down this, so trace of x square is just summation lambda I square, and then the trace of xi fourth will be summation lambda I to the power fourth. So basically this polynomial gets replaced by v of lambda I function. Okay. So this is this part, and the Jacobian part, it remains exactly the same as before, Gaussian case, because Jacobian does not depend on this. Jacobian is just comes from the volume element. Okay. So this is, remember that in our trivial example, when I make Gaussian, so when you make polar coordinates, this becomes e to the power minus r square, but the Jacobian is r dr d theta, no matter what this is. Okay? The Jacobian doesn't depend on this choice. And so in general, so this is the general formula, where I put this index beta. This index beta denotes, is called the Dyson index. And as we saw here in this example, Gaussian case, and in general for arbitrary these things, that beta has quantized values. For rotational invariant ensembles. And depending on the ensemble, the value of beta changes. So beta equal to 1 for orthogonal ensemble, beta equal to 2 for unitary ensemble, and beta equal to 4 for symplectic ensemble. Okay. Now, you might ask, is it possible to obtain other values of beta for some ensemble? Okay. The answer is yes, not for rotational invariant ensembles, but there are very special type of matrices called the Dimitru-Edelman matrices. Maybe if I have time, I'll talk about that later. This is a very recent work actually. So these are not rotational invariant. This is a very special type of random matrices, not rotationally invariant. Very special type of matrices, and for these matrices, it turns out it's a very difficult thing. So these matrices, that means they are part of Wigner matrices, meaning independent entries, but non-identical entries. And so only for that particular choice of this particular matrix, it turns out that you can actually calculate the joint distribution of eigenvalues and eigenvectors. Of course, they do not factorize because it's not rotational invariant. And then you have to integrate over the distribution of eigenvectors to obtain the distribution of eigenvalues, and that's what they did. So maybe I'll just write down the matrix just for fun. It's a very, very non-trivial work. Let me see what I have here. actually drawn from what is called the chi-square distribution. So you have a matrix like that. I mean, roughly speaking, I don't remember the details now, but it's a matrix which is a tri-diagonal matrix. Okay, so you have the diagonal elements non-zero, and you have these guys are non-zero, and the rest is zero. So it's a tri-diagonal matrix. So you choose each element independently, but from distribution, which varies as you move along these lines. So the distribution of this guy is different from that guy, which is different from this guy, and which is different from that guy. So they're independent but non-identically distributed. Non-identically distributed, but distribution is generally from what is called the gamma distribution, which has a parameter, okay, and so this parameter is some parameter, positive parameter beta. So beta characterizes these distributions, okay? And it also depends on the location of the entries. So for such a complicated matrix, they were able to make this change of variable, that is going to eigenvalues and eigenvectors. Of course, it depends on both of them. They are coupled now, eigenvalues and eigenvectors, because this is not rotational invariant. So then you integrate over the eigenvector degrees of freedom and calculate the joint distribution of eigenvalues. And what they found is that the joint distribution of eigenvalues in that case. So again, I'm not telling you exactly what these distributions of each individuals are, but basically up to this normalization constant, to the power beta, but you see that beta now is a continuous parameter, positive parameter. So coming from rotational invariant principles, beta only has quantized values 1, 2, or 4. But for such matrices, you can actually, so this is a very non-trivial result, so due to Dimitrov-Needleman, okay? And so you can actually generate a joint distribution of eigenvalues with arbitrary beta here, and with arbitrary Dyson index, arbitrary positive Dyson index. So, and there's a physical meaning of this beta, which we will discuss. How much time do we have? 15 minutes? Okay. So now let's think of, okay, so what did we do so far? We have carried out the first step, right? So from here, our goal was to calculate the joint distribution of eigenvalues, and we have done that. Okay. So this is done. And the joint distribution generally for rotational invariant ensemble, it has this form, okay, with beta equal to 1 to 4, or if you take the Gaussian case but with a very weird example like that, but generically let's say it's of this form. So let's think of the Gaussian first. Where this beta is positive. And for simplicity, I can rescale the eigenvalues, just going to lambda I to, let's say, square root of beta lambda I. If I make this rescaling, so then I can take under this rescaling, I can take out the factor beta here. And the reason I'll do that in a minute will be clear. So and this scale factor here just gets absorbed in normalization. So let's take this as our main result, joint distribution of eigenvalues. So first step is done. Okay? So this is the analog of, if you like, deriving Gibbs-Boltzmann distribution in equilibrium statistical mechanics. Now the next step comes, and that's where, so far it was only mathematics, okay? So now the physics will come in, that given this joint distribution, what can I say about some properties of these lambda i's? Now, there's a very beautiful physical interpretation of this distribution here, which I want to tell you before we finish today. This object first. What is this? So this is a joint distribution of eigenvalues. So it has to be, so what is Zn? This guy has to be normalized, right? That means if I integrate, this is a probability distribution. So if we integrate over all possible eigenvalues, going from minus infinity to plus infinity, it should be equal to 1. So that means this Zn here is, so if I just substitute this object there, so you see that Zn is just the integral, it's a multiple integral. Times this object. Okay? So this is called the van der Waals determinant. Because you can write down this as a van der Waals. Everybody knows van der Waals determinant? Okay, if you don't know, that doesn't matter. This is a name, van der Waals. Okay. Now this guy here, okay, first thing you notice that the probability distribution, I mentioned that last time, that this factor, if I did not have this factor, then they would completely decouple. Okay? There will be no correlation between eigenvalues. Because of this factor here, there is a correlation. Joint distribution does not factorize into individual distribution. Okay? So this guy encodes correlations between eigenvalues. And what kind of correlation? So you see that when two eigenvalues, so these eigenvalues are like this on real line. So when two eigenvalues come very close together in some configuration, the probability of such configuration is very, very small, because this guy is some positive power to the power beta. That means it vanishes when the two eigenvalues come close together. So that means probability is very small, which means that they don't like to come very close to each other. Okay? So this is what is called level repulsion. In levels, they repel each other. Now, more precisely, so I can write this term by raising it to logarithm. Is that clear? Is that clear to everybody? I can always write y to the power beta as e to the power beta log y. Right? That's what I'm doing there. Huh? There is no? Where? Yeah, I said, I rescaled. Remember, I said that I just rescaled this in order to get this beta, just to write, okay? And the reason will be very clear in a minute. Okay? So this term here, I can always write it this way. Agree? Beta by 2 summation log lambda j. And this factor 2 comes because here it was j less than k. So I include the j bigger than k and divide by 2. So then this has exactly this. Okay? So now what is this? So I can write down this. You see, you can write this as beta E lambda I. And what is this E lambda I? So the E lambda I is a function of all the lambda i's, which is half times summation lambda I square minus half times okay. Let's look at it for a minute. What is this? So this is, all of you know equilibrium static. So this is as if the Boltzmann weight. So if I think of this beta as inverse temperature, so this is exactly the Boltzmann factor, the Gibbs-Boltzmann factor, e to the power minus beta e. This is just the partition function of a gas of particles whose positions are denoted by lambda 1, lambda 2, lambda 3, lambda n. So what I have is the following.
This type of system is for neural system shows that
Don't complicate things. I'm going slowly. We'll see that later. So what is this object here? So if I think of any particular configuration of these lambdas, so you can think of them as point charges sitting on a line, okay? And they are interacting. And this is the total interaction energy. So it has two parts. There's this part and that part. What is this part? This part says that these charges, they all feel an overall confining potential. I'm not drawing it very well. Okay, so this is a quadratic confining potential. Okay, so the charges are sitting there. So all of them are feeling this external potential. Okay? So if you put them, each of them feels half lambda square. So this is the total potential energy due to the confining harmonic potential. Okay? So these guys will try to put all of them near the energetically favorable when they all come very close to the origin. But what about this term? Yeah. So this term says that there is a repulsion. This is exactly analogous to this in this language here. That there is a repulsive term. So between any pair of particles, okay, they don't have to be nearest neighbors. Any pair of particles, there is a long-range Coulomb interaction. Okay? And they are repelling each other by this logarithmic interaction. Okay? This is repulsive because of this sign here. Okay? So you see that when lambda j minus lambda k becomes very small, okay, this guy becomes log of very small quantities minus of very large quantity. So the energy actually increases. Okay? So therefore this is a repulsive term. Okay? Yes. No, I'm not saying, did I say anywhere Coulomb interaction? Long range. And all I'm saying is long range point particle. I have not said yet Coulomb interaction. Okay? So you can just interpret this system of particles as point charges, okay, which are sitting in an external potential, okay, and they're repelling each other by these long range logarithmic forces. Okay? Now, whether it's Coulomb or not, you know all that in 2 dimension, if you have a Coulombic system, in 2 dimension the Coulomb charges repel each other by logarithmic interaction. In 3 dimension it goes like 1 over r. In general it's 1 over r to the power b minus 2. Okay? So in 2 dimension there is a logarithmic interaction. But so, you can interpret them as Coulomb charges, but then you have to be very careful because these are actually charges, even though they are interacting with a 2D Coulomb interaction, but they are confined on a 1D line. This is a very special kind of charges. So imagine that in a 2-dimensional world, I have some point particles, electrons. Okay? So they are repelling each other by Coulomb. But I confine them, okay? I make them constrained to stay only in one line. I don't give them the space to move around. Okay? So then this system corresponds to that. So this is a 2D Coulomb charges living on a 1D line. So there are two terms to the energy which are competing with each other. So what is this guy trying to do? External harmonic potential is trying to push all the charges towards the origin, because that will be the energetically most favorable. But the Coulomb repulsion, of course, they don't want the charges to come to each other. They repel each other. They would like to push the charges apart. So these two forces are going to compete with each other. So external potential is trying to push it towards the origin, and the Coulomb repulsion is trying to spread them apart. Okay.
Can also be attractive for land.
It comes from this. Now, I'm not assuming anything. Don't bring things from outside. And I just started from here, right? I'm just interpreting my object as a Boltzmann, as a partition function of a Coulomb gas, a special type of Coulomb gas. Okay? These are not physical objects. This is an interpretation. What is your precise question?
Lambda J minus lambda K that becomes greater than 1 and their interaction will become
No, but at long range. But basically, think of if you don't think long, think in terms of this. It just says that when they are far apart, of course, it's an increasing function. Okay. But when they are coming close, when lambda 1, when they are very close, the probability becomes very small. Of that happening. So they can't come very close to each other. They like to stay spreaded. Okay. Whereas this guy here is trying to push them towards the origin. So then you want to interpret this partition function as this is the partition function of that Coulomb gas, a special type of Coulomb gas in presence of a harmonic potential. And so the first question is that what is the equilibrium distribution of these charges? So I have two competing interactions. What's the minimum energy configuration? What's the configuration in which this system settles down? Okay. You can imagine that if you did not have this term, equilibrium configuration would be basically everybody would be at the origin, essentially. It would be a delta function at the origin. I mean, not delta function, but Gaussian function at the origin. Okay. Now, because of this, there will be spread. Okay. Or alternatively, if you did not have this term, then because of the spread, they will be far apart from each other. Okay. So these two are competing interaction, and because of this competing interaction, the best possible configuration for the system, which is basically the configuration of lambda is that maximizes this partition function or minimizes the free energy, is going to be something. So they will settle down. You will find a lot of charges near the origin, and then there will be little smaller charges here. So you want to calculate the profile of density. So density profile. So what is the average density? What do I mean by density? So I want to calculate this object, rho lambda for a given n. So what is this object here? So this delta function here counts just how many eigenvalues are there between lambda and lambda plus d lambda. So rho lambda n. So when I take the average now, average with respect to this Boltzmann weight, so this is going to be the average density of particles. So normalized to 1, okay? So this is just tells you that, this delta function counts when, so you look at between, let's say, lambda and lambda plus d lambda in your space, in this little box here, and you ask, what fraction of particles are there? Okay? What's the average fraction of particles living in that little box? Because you see that if I integrate over lambda over the full space, by definition this will be 1 over n. Then I have I equal to 1 to n, and integral of delta function is just 1. Okay. So this will be 1. Okay. So this is just the fraction of particles between lambda and lambda plus d lambda. The total fraction, of course, is 1. Okay. So it just counts what's the fraction out of n particles, how many charges are there, and that will give an idea of what's the equilibrium profile of these charges. Okay. And we'll see what this form is maybe in the next lecture, and we'll try to calculate, starting from this, you'd like to calculate what's the average density of states. So this is just the density of states normalized to 1. Okay? And so right now my program is that given this, so we know this, we have derived this. So now I'm going to start from this, and I'm going to start from this and calculate observables of properties. And what I'm saying is that in order to calculate such observable properties, I notice that I can interpret this as a statistical mechanical system, which is long-range interacting particles sitting in an external potential. And we have a lot of experience with statistical mechanics, equilibrium statistical mechanics. So I have a problem of equilibrium stat mech now. So I can actually calculate the full partition function and other objects and free energy, and from that I will be able to, should be able to calculate, I mean, in principle, all kinds of other observable properties of this gas. So all I have to do is to look at some equilibrium properties of this gas, basically. For example, the spacing distribution, or the largest eigenvalue, or the average density of states. So these are different observables. So the next 3 lectures, my program will be starting from here. I want to calculate such macroscopic property, I mean, the observable properties of this pool of gas. Okay? And here the physics comes because we are experienced in our equilibrium stat mech. We can actually use our physics techniques to solve these problems. You don't have to do mathematics anymore, basically. I mean, you can do mathematics, of course, and you have to do at some points, but at least physics will take us very far. Okay? So you can derive the large N properties, because large N is what is interesting. So large N properties of this system can be derived quite easily, and large N is what matters. I mean, because in the main point is that in the large N limit, you know, even though I mean, this partition function here, see what happens is that large N limit is always useful in physics. I mean, Sumit will talk more detail about it later, you will see, because you can actually do saddle point approximation to this integral. So because of saddle point approximation, which is, you know, very useful and simple, it tells you a lot about what's going on in the system. Okay? And we'll see that explicitly tomorrow when I calculate this average density of states. Okay.
How to do the Gaussian guess that the density is
Very bad.
because of the interaction?
No, yes, absolutely. This interaction, see, without the interaction, it will be exactly Gaussian. Okay, because they're independent. Okay. The moment you put this thing, it's a complete change from Gaussian. And because there is a conflict, you know, there is the repulsion tries to spread them apart. Okay. So in fact, it will witness semicircular.